say we take so we started with near some inert gases, so where the electronic cell is completely full, and though it will be diamagnet. If you take nitrogen, for example, so it is not completely full, the P cell. But normally we don't work with nitrogen atom, but rather nitrogen molecule. And then when you fill the orbitals, so what we'll observe is again the total the electronic cell of the nitrogen molecule will be completely filled, and nitrogen will be diamagnetic. But if you take an oxygen molecule, and then when you fill up the electronic cells, so you will see that this 2p, so oxygen will be 1s2, 2p, 2s2, 2p4. And in this case, you will see that when you take the molecule, so the orbitals are filled in such a way that you will have incomplete this pi 2 pi p orbitals, and that's why it will be paramagnetic. Okay. So let's take example of, let's say, titanium. So titanium is 22. Okay. So here it will be up to argon will be filled, and then it is 4s2 3d2. So now if you look at the 3d orbital, so you have 5 d subcells, and basically your 2 are filled and the rest are empty. So here the d orbital is not completely full. So that means it will be paramagnetic. So in this, atoms, so from titanium up to copper, for example, up to copper. So they are called like transition metals. Transition metals. And in this row only, you will find these atoms. So so let's say now it is like you can tell whether an atom will be paramagnet or diamagnet looking at the electronic structure. But in this like periodic table, this transition metals. So if you take cobalt, iron, and nickel, so they are only the ferromagnetic ones. So rest are paramagnetic or maybe diamagnetic. So we will take, so this is like about atoms or molecules. But what about when we make compounds? Okay, that is more interesting. So now if you take compounds of, let's say, one of these transition metals. So there are some compounds like salts, for example. So in chemistry they are used quite a lot. So different kinds of salts with one of the elements from this transition metal group. So those salts, so one example I will give you, which is given in the book as well. Chromium 12H2. Okay, so this is a salt where this chromium is basically from the transition metal group, and the valence state is it's in 3+ state, and this salt is paramagnetic. Okay. So you can, so also if you remember the periodic table, I also mentioned that we have something some materials which are known as rare earth materials. So if you go to the lanthanum series, so starting with lanthanum, uh, you will have, like you have gadolinium, dysprosium, hafnium in that series in the periodic table. In that, those materials are actually called rare earth. Okay. So why rare earth? It's because it is definitely, I mean, not rare, but relatively rare, difficult to find in nature, and also it is difficult to extract these, uh, get them separated, because they are very similar in terms of their chemical behavior. So therefore, it is very difficult to extract them and make them separate, and that's why they are actually called as rare earth. And nowadays, in fact, many of these materials are actually rare, not so easy. Those materials are also very interesting from magnetism point of view. So these transition metals are normally called as 3D transition metals, because once when you go from titanium to copper or zinc, so you basically fill it up with electron in the 3D orbital. The rest are already full. So these are called 3D transition metal. So they are like in magnetism, they are very important. Now, if you look at similarly in magnetism, this rare earth, these are also very like one of the few atoms which actually give rise to very high magnetic moment, and that's why they are also used quite a lot in magnetism. And so if you look at the electronic electronic cell, so it is normally, it's like, let me write down on the top again. So this is transition. Okay, so I will write down here. So I take an example of a famous material in magnetism. It is gadolinium. Okay, so it is gadolinium. Now the electronic cell is, so you have xenon, then you have 4f7 and 5d1, 6s2. So this is the electronic distribution in the gadolinium. Now this 4f orbital, so when you look at that, so basically, so this one will be 5, 6, 7, right? So you fill it up like this using your Hund's rule and Pauli exclusion principle. So this 4f is responsible for the magnetic moment. So this is not fully filled. So when you fill up the electrons, so typically in the lanthanum series, so you fill the f cell, so 4f cell. So you go like 4f1, 2, 3 up to 4f14. Okay, so this is how you have this 14 elements. So these are called this rare earth series, or since the magnetic moment comes from this 4f orbital. Okay, and these are depending on whether they are filled or not filled. And since this magnetism comes from 4f, so they are called as 4f elements, 4f magnetic elements. Just a moment. Okay, so they are called as 4f magnetic elements. So you have this 3D transition metals, and you have 4f, your rare earth. Metals. So in this series, so gadolinium is actually in this series is ferromagnetic, and the temperature, Curie temperature is up to 92 Kelvin. So others have magnetic moment, but they are mostly paramagnetic, or they become ferromagnetic when you go to low temperature. So there is dysprosium, neodymium, hafnium. So all these, they might become ferromagnetic at low temperature. So this is about the elements or atoms present in the periodic table. So, but in general, we use, let's say, something most common is what you use in metal, right? So metal and these atoms are very different, right? Of course, a metal like a copper will be made up of copper atoms, but the behavior of a copper metal and a copper atom is very different. Or let's say you take aluminium, or you take iron. So all these materials are different in their atomic form and in their when they form a metal. So what is interesting about metal? So metal, why they are interesting? So because they have something called, they are also called as conductors, right? So they conduct electricity, so which you use quite a lot. So and this conduction comes from the electrons. And these electrons which participate in conductivity are known as your free electrons or conduction electrons. Okay. So when you look at a metal, so an atom in a metal, it behaves in a different way, and the metal you can say as, so your ionic core, so which will have your nucleus plus core electrons, and then plus your conduction electrons. Okay, so this is how you can, it is different from an atom. So in a metal, just you take the copper, so atom will have some electronic cell, and they are all, so either they're filled or partially filled, okay, like that. But in metal, so you distinguish, you say that it is like a regular arrangement of atoms. First of all, metal consists of many atoms, so not one single atom. So it consists of, so maybe you 10 to the power 23 or so 10 to the power 30 atoms. And then when you look at the metal as a whole, it's like it has this ionic cores which are really attached to fixed regular points. Okay, so this is, let's say you have atoms which are regular arrangement in 3 dimensions. So it is not 1 dimension or 2 dimension, but it is arranged in 3 dimensions along x, y, and z. And then you have these free electrons, single, maybe 1 electron or 2 electron, so which are actually free and they are free to move in the metal. And that's why since they are free to move, so they will give rise to this conductivity, right? So that is what a metal is. And that's why the magnetism that arises from metals is also very complex. It is not so easy or straightforward. But we will only look at or simplify the things. So what we can now say, so since we divide it into like an ionic core, like your core electrons and conduction electrons, so what we can say is the magnetism in metal can come from the metal, which is the magnetism in metals. So you can say that the contribution is from core electrons and plus your conduction electrons. So now we just separate these two. So we say this is magnetism can come from the core electrons or conduction electrons. So I neglect the nucleus because when we saw that the magnetic moment of your nucleus is normally negligible. So most of the magnetic moment actually comes from electrons. It is due to electrons. Okay. So now, so this core electron, so that can have. So these are like just like stationary, almost like atom-like, right? So the conduction electrons are moving freely, but your core electrons are just like your normal atoms. So now, so you can have, and these core electrons are also all are filled cells, right? So they are completely full. So if you look at the core electronic configuration, so they should be completely full. So there will be no partial occupation or partial filling. So it is completely filled, and that's why it is going to give rise to only diamagnetic contribution. So it only will have a diamagnetic susceptibility. So it will behave like a diamagnet. But your conduction electron, so conduction electron can have like a paramagnet. Also can also behave like a diamagnet. So remember one thing. So in magnetism, so we say that all materials are magnetic. So it may be diamagnetic, or it can be paramagnetic, or it can be ferromagnetic or something, but it is magnetic. So anything when we talk about is magnetic. So therefore you will have a paramagnetic contribution, diamagnetic contribution from the conduction electrons, and diamagnetic contribution from core electrons. So we can simplify it in such a way that if we write that magnetic moment of a metal will have diamagnetism from core electrons, then diamagnetism from this conduction electrons, and plus, or I should say, oh yeah, okay, so that is fine. So then paramagnetism from conduction electrons. Or instead of saying mu of the magnetic moment, I should say susceptibility. So that is conduction core electrons plus diamagnetic susceptibility from conduction electrons and susceptibility from conduction electrons. So now this is a competition between these contributions, three contributions, and depending on which contribution is larger, so that metal will be diamagnetic or paramagnetic. So diamagnetic contribution is large, so this is a diamagnet. So example will be example of diamagnetic metals will be copper. This is diamagnetic. Even for example gold or silver or tin. So these are diamagnetic. Now paramagnetic. So this all depends on which contribution is larger. So it could be aluminium or magnesium. Okay. So these are all, or titanium, for example. Okay. So this could be, or even let's say palladium, platinum, really good metals. So these are all paramagnetic in nature.